For all our ambition, all our rockets, all our cosmic dreams, humanity has barely stepped off its front porch. We imagine ourselves as explorers of the universe, heirs to a destiny written in the stars. Yet the truth is far more humbling. We are confined, tethered, bound to a tiny island of light orbiting an ordinary star. Every distant galaxy, every glittering nebula, every world we might one day call home lies impossibly far beyond our reach, and the universe does not care how desperately we want to explore it. The speed of light, the ultimate speed limit of reality, sits before us like an invisible wall. Our fastest spacecraft would take tens of thousands of years to reach even the nearest star. Radiation lashes at anything traveling through interstellar space. Fuel requirements rise exponentially with speed. Space itself expands faster than we can ever hope to travel. The cosmic ocean is vast, and we are a species stuck in a leaky wooden boat. Yet the question lingers, whispering in the back of every dreamer's mind. Are we truly trapped? Is our solar system the boundary of our existence, or just the first barrier we must break? Humanity stands at an extraordinary crossroads. We are clever, resourceful, stubborn creatures. But the cosmos is not a friendly place. It is cold, indifferent, governed by laws that do not bend for any species, not even one clever enough to ask if it can outrun them. If you love journeys into the unknown, if you find meaning in the vastness above us, consider liking this video, subscribing, and tapping the notification bell. It helps bring more curious minds along for the ride, and it ensures you never miss the next step into the cosmic frontier. Before we imagine what lies beyond the sun's frontier, we must understand the invisible cage we are caught within. Only then can we decide whether it can be opened or whether it will remain sealed forever. Interstellar space is not empty. It is a graveyard of obstacles. Vacuum, radiation, dust, and distances so colossal that they break the human mind's sense of scale. Even the nearest star system, Alpha Centauri, sits more than 4 light-years away. That is 40 trillion kilometers. Numbers that large lose their meaning. If Earth were a single grain of sand, Alpha Centauri would still be 4 kilometers away, and in between, nothing but darkness. Our fastest spacecraft, the Voyager probes, drift at speeds of around 17 kilometers per second. At that pace, reaching Alpha Centauri would take more than 70,000 years, longer than recorded human history. Civilizations would rise and fall before the ship ever arrived. Even a craft 10 times faster would barely make a dent in the cosmic distance between stars. This is the first wall that cages humanity. Space is enormous in a way evolution never prepared us to comprehend. Our brains evolved to navigate forests, rivers, mountains. Our ancestors crossed continents and oceans, believing that the horizon marked the limits of the world. But the universe laughs at horizons. It draws them billions of kilometers beyond our reach. Even the light we see in the night sky is a reminder of our confinement. Those stars shimmer not as destinations, but as time capsules. Their light began traveling long before our species learned to walk upright. We are spectators of the cosmos, not participants, our eyes locked on a show whose stage we cannot yet step onto. And until we break the tyranny of distance, every star in the sky might as well be a painting on an unreachable ceiling. Humanity's second barrier is not a matter of engineering or imagination. It is the universe's own law. Nothing with mass can travel faster than the speed of light. No matter how powerful the engine, how advanced the technology, or how desperate our will, the laws of physics draw a line we cannot cross. To accelerate a ship to even a fraction of light speed requires energy comparable to the annual output of entire nations. Pushing closer to the cosmic speed limit demands exponentially more power. At 90% the speed of light, the mass of the ship effectively doubles. At 99.9%, it multiplies dozens of times over. The faster you go, the heavier you become, dragging against the universe itself like a swimmer caught in cosmic molasses. And even if we somehow solve the energy problem, there is another danger. At high relativistic speeds, every particle of dust becomes a bullet. Every atom of hydrogen becomes a beam of lethal radiation. Traveling near light speed would turn the interstellar medium, normally harmless, into a torrent of ultra-high energy collisions. A human crew wouldn't survive seconds of that punishing bombardment. The speed of light isn't just fast, it's final. A boundary that protects the structure of reality but imprisons civilizations within their star systems. It is a limit that defines the shape of cosmic ambition. And until we understand how to bend, cheat, or rewrite the rules that govern motion, interstellar travel remains a distant dream. Even escaping our own solar system demands unimaginable energy. Rockets today rely on chemical fuel, good enough to push satellites into orbit, but far too weak to propel a spacecraft to another star. Chemical propulsion is like trying to cross the Atlantic with a box fan taped to the back of a raft. You can move, but not meaningfully. To reach neighboring stars within human lifetimes, we would need engines thousands or millions of times more powerful than anything we have ever built. Nuclear propulsion promises more thrust, but still falls far short of interstellar capability. Fusion engines could, in theory, change the equation, but harnessing and containing miniature stars inside a spacecraft remains a challenge at the very edge of physics and engineering. And then there's fuel. The faster a ship goes, the more fuel it needs. The more fuel it carries, the heavier it gets. The heavier it gets, the more fuel it needs again. A vicious loop known as the tyranny of the rocket equation. A ship capable of reaching nearby stars would need an absurd, almost comical amount of propellant. Entire asteroids might need to be converted into fuel just to accelerate a single craft. Even the most promising solutions, light sails pushed by powerful lasers, shift the energy burden from the ship to the civilization launching it. But such a system would require power output on the scale of global grids working in unison. Humanity, at present, is not even close. Energy is the true currency of cosmic exploration, and right now, humanity is almost broke. Even if humanity solved the problems of speed, energy, and distance, there remains another silent adversary, waiting in the darkness between stars: radiation. Our solar system has a natural shield, its magnetic field, and the protective bubble of the heliosphere. But once a spacecraft crosses that boundary, it enters an arena governed by deadly cosmic forces. High-energy particles race through interstellar space at near light speed, born from supernovas, black holes, and ancient cosmic collisions. These particles easily penetrate metal hulls, electronics, and human bodies. A ship traveling between stars would be bombarded constantly, its crew subjected to radiation levels far beyond what any human has ever experienced. Prolonged exposure can damage DNA, destroy cells, and trigger cancers. Even the spacecraft's circuitry risks being fried by the relentless storm of charged particles. To survive the interstellar void, we would need shielding far thicker and heavier than anything used in current spacecraft. But heavy shielding increases mass, which increases fuel requirements, which slows the journey and makes the entire mission harder. Engineers call this the radiation paradox. Building a ship strong enough to endure the cosmos makes it too heavy to leave home. Some future concepts imagine magnetic shields or plasma bubbles that could deflect cosmic rays, mimicking Earth's magnetosphere. Others propose embedding spacecraft in layers of water or hydrogen-rich materials to absorb radiation. But these technologies remain experimental, untested, and theoretical. For now, the interstellar void is a crucible of hazards humanity is not yet prepared to endure. To cross the distances between stars, a civilization must learn not just how to travel fast, but how to survive the invisible storm that waits along the way. Even if we built a spacecraft capable of surviving the cosmic radiation and reaching extraordinary speeds, there remains a problem far more ancient and intimate: the fragility of human life. Our bodies are not designed for centuries. Our minds are not suited to generations spent inside metal walls, and the nearest habitable worlds may be dozens, hundreds, or even thousands of light years away. At current technological levels, any journey beyond our solar system would span multiple human lifetimes. Crews would either need to be replaced by their children and grandchildren, or preserved through suspended animation, two concepts that raise profound ethical, biological, and psychological challenges. A generation ship would be a floating world with its own ecosystem, culture, and society, evolving independently of Earth. The crew born aboard such a ship would never see the planet their ancestors came from. For them, the destination would be a story, not a memory. Their entire existence would unfold in the narrow corridors of a vessel drifting through the void. Maintaining morale, population stability, and technological capability across centuries is a challenge no civilization has ever attempted at such a scale. Suspended animation or cryogenic sleep offers a different dream, placing humans in hibernation and waking them only upon arrival. But freezing a human body without destroying its cells remains beyond our capabilities. Even if the technology existed, the risks would be enormous. A single malfunction across centuries could doom an entire mission. Some propose replacing the crew entirely with machines, robots or AI explorers capable of patience that humans lack. But that raises its own question. If machines can explore distant stars more effectively than humans, does humanity ever truly leave the solar system, or do we simply send our metal proxies to do the dreaming for us? Until we solve the limitations of our own biology, the stars remain suspended behind a barrier our bodies were never designed to cross. Even before confronting interstellar space, humans must escape a far older and more familiar adversary: gravity. Every rocket launched from Earth begins with a desperate battle against the planet's grip. Most of a rocket's mass is fuel needed just to lift the fuel required for the next stage of flight. The energy cost to escape Earth's gravity well is immense, and it dictates every aspect of our spacefaring ambitions. But Earth's gravity is only the beginning. The Sun itself holds our world in a deep gravitational well. To truly leave the solar system, a spacecraft must claw its way out of the Sun's pull, requiring velocities far greater than escape from Earth alone. This is why so few probes have ever achieved true solar escape speed, and why even the ones that have, like Voyager and Pioneer, drift slowly outward, far too weak to journey between the stars at any meaningful pace. Gravity is a silent warden. It keeps the planets in their orbits and locks our species within the Sun's domain. To break free, humanity would need technologies far beyond chemical rockets. Concepts like ion engines, nuclear pulse propulsion, antimatter drives, and solar sails offer possibilities, but each carries its own impossibilities, dangers, or technological hurdles. Even if a spacecraft escaped the Sun's gravity, its initial speed would still be insignificant compared to galactic scales. Within the vastness of the Milky Way, our solar system is a single drop of water clinging to the inside of an endless cosmic cavern. To leave it behind, we must look beyond brute force and into a future where we reshape gravity itself or slip through space-time in ways we have not yet learned to imagine. Until we overcome the gravitational chains that hold us close to our star, humanity remains a prisoner in the place it calls home. Beyond the solar system lies a realm more hostile than any environment humanity has ever faced. It is not simply dark, it is a darkness so profound that light itself becomes rare. It is not merely empty, it is an emptiness that stretches for trillions of kilometers, with no landmarks, no resources, and no second chances. Interstellar space is a wilderness where the familiar rules of survival vanish. Temperature drops to near absolute zero. The nearest source of heat is the faint glow of your own ship. Micrometeorites, tiny fragments of rock and metal, drift invisibly through the void at incredible speeds. A grain of sand striking a ship at significant fractions of light speed would hit with the energy of a bomb. Even the rare collisions with dust can erode hulls, tear through shielding, and shred delicate instruments. There are no repair stations, no resupply ships, no rescue missions. A spacecraft venturing into interstellar space must be perfectly self-sufficient, built to withstand centuries of operation with redundancy for every critical system. Life support must function flawlessly. Power must remain stable despite the incredible distance from any star. Food production, recycling systems, propulsion, and navigation all must endure a journey longer than the rise and fall of civilizations. Humans evolved in environments with gravity, atmosphere, and day-night cycles. Extended isolation in deep space would strain the human psyche in ways we cannot yet predict. Anxiety, sensory deprivation, claustrophobia, the burden of responsibility, these would follow a crew like shadows cast by the very stars they chase. This is the harsh truth. Interstellar space is not simply far away, it is fundamentally incompatible with human life. And until we reshape ourselves or our technology to meet its requirements, it remains a barrier as formidable as distance or physics itself. When we look at the night sky, the nearest stars feel close, almost reachable. Their light twinkles as if inviting us to cross the gulf between worlds. But this is an illusion created by the limitations of our perspective. Every star we see is separated from us by vast emptiness, and even the ones considered nearby are unimaginably distant. Take Proxima Centauri, the closest star to Earth. Astronomers call it our neighbor, but neighbor is a misleading word. A neighbor is someone you can visit. A neighbor is someone you can speak to. Proxima is a star whose light takes over 4 years to reach us, even while traveling at the cosmic speed limit. If Earth orbited Proxima and we sent a radio message home, it would take nearly a decade for the round trip, longer than many human relationships. And what lies around these stars? Potentially habitable planets, yes, but we have only faint clues about their true nature. Are they scorched wastelands, frozen spheres, worlds bathed in deadly radiation from their parent stars? We don't know, and we cannot know without sending probes or crewed ships across interstellar distances. We speak casually about exoplanets as though they are destinations waiting to be explored, but for now, they are stories told by dips in starlight and subtle shifts in spectra. They are shadows, not worlds, dreams, not destinations. They sit on maps drawn by telescopes, not by explorers. Every nearby star is a reminder that the universe is far larger than our imaginations. Close is not close, near is not reachable, and until we reinvent what it means to travel, the stars remain beautiful illusions painted across a sky we cannot reach. Time is the final enemy of interstellar travel, and it may be the most unforgiving of all. A journey to another star is not a single mission. It is a commitment that spans decades, centuries, or even millennia. In that time, nations will fall, languages will change, entire generations will be born and die. The Earth the travelers left behind may not resemble the one they return to, if they can return at all. Even the most durable spacecraft will age, metals will fatigue, electronics will degrade, radiation will slowly erode every system. Micrometeorite impacts, tiny but relentless, will scar hulls and damage instruments. Without constant repair, without the hands of skilled engineers, the ship becomes vulnerable to failures that accumulate across decades. Time is the ultimate saboteur. For the crew, time is even more complicated. Human lives are brief compared to cosmic distances. A journey that lasts centuries would require people who never see the stars they're traveling toward, and whose children will be raised aboard a ship they did not choose to inhabit. Culture would evolve in isolation. Beliefs, social structures, even the sense of identity could drift far from the civilization that launched them. And on Earth, time does not stand still. While a ship drifts through space at a fraction of light speed, technology continues to advance. A century after launch, humanity might develop faster propulsion systems, meaning a second mission could overtake the first. The sacrifice of the original crew becomes a relic of outdated technology, rendered obsolete by progress they could never anticipate. Time bends civilizations. It erases intentions, it reshapes futures, and in the scale of the galaxy, human time is little more than a flicker. Until we learn to extend life, preserve technology indefinitely, or outpace the erosion of years, time itself stands as a nearly insurmountable wall between us and the stars. Despite the walls that surround us, distance, radiation, gravity, biology, time, humanity is not a species that accepts confinement easily. Every generation has sought to break the boundaries of its age. We crossed oceans that seemed endless. We scaled mountains that seemed unconquerable. We split the atom and walked on the moon. History shows that when faced with the impossible, humans do not retreat. They innovate. And so the idea of interstellar travel has sparked some of the most radical concepts in scientific thought. Ideas that bend reality, that challenge the edges of physics, that ask, what if the rules we believe in are not the only ones? Warp drives propose stretching and compressing space-time itself, carrying a ship like a wave on a cosmic tide. Wormholes imagine shortcuts through the fabric of the universe, connecting distant stars through tunnels beyond our physical understanding. Antimatter engines promise near light-speed travel by harnessing energy from the annihilation of matter itself. These ideas sound like science fiction, but so would rockets, satellites, or nuclear power to humans a century ago. To pursue such breakthroughs requires not just technology but courage. Courage to confront the unknown and redefine our place in the cosmos. The frontier of the impossible is not where science ends, it is where imagination begins. And in that frontier lies the only real hope of breaking free from the solar system's grasp. Humanity has always lived on the edge of the impossible, and that edge may be the birthplace of our interstellar future. If humanity ever hopes to leave the solar system, we must evolve, not biologically but technologically, socially and intellectually. An interstellar civilization must be far more advanced than anything humanity has yet achieved. It must possess energy sources that make today's power grids look like campfires. It must build structures in space the size of cities. It must create ships capable of sustaining life for centuries, or machines capable of exploring without fatigue. Such a civilization would harvest energy from space itself. It might build vast solar arrays beyond Earth's orbit, or tap into fusion reactors that mimic the power of stars. It could construct habitats where millions live in artificial gravity, farming, working, and raising families beyond Earth's surface. Its ships would be ecosystems, self-sustaining, balanced, resilient. To maintain interstellar missions, humanity would need to embrace long-term thinking on a scale unprecedented in our history. Nations would need to cooperate across generations. Knowledge must be preserved flawlessly, passed on without distortion. The motivations for exploration must endure through centuries of cultural change. A civilization capable of interstellar travel is one that no longer fears scarcity. It no longer burns resources in desperation. It no longer thinks in election cycles or quarterly profits. It thinks in millennia. It plans for futures shaped by stars, not borders. This transformation is not guaranteed. It is a choice. A path humanity may take if it decides that exploration is worth the effort, the risk, and the sacrifice. To reach the stars, we must become something greater than the species that first looked up at them. So is humanity trapped in our solar system? For now, yes. The barriers are vast, unforgiving, and woven into the structure of the universe itself. Distance dwarfs our technology. Radiation threatens our biology. Time stretches longer than our civilizations. Gravity binds us to our star, and the void between worlds is as hostile as any environment known. But the story does not end with limitation. It begins with possibility. Humanity has always lived beneath impossible ceilings. We broke the sound barrier. We split the atom. We transformed the night sky from a realm of myths into a map of galaxies. Every age of exploration began with a boundary that seemed permanent. Every breakthrough was born from refusing to accept the limits imposed by nature. The stars are not closed to us. They are simply far away. The solar system is not a prison, it is a cradle. And no cradle holds its children forever. One day our descendants may stand on the shores of alien worlds, watching new suns rise. They may look back at the Milky Way from places we cannot yet imagine. They may travel through space-time in ways that today seem impossible. And when they do, they will know that the journey began here, with the first species that dared to ask whether it was truly trapped and refused to accept the answer.